Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions, to promote the use of the best available methods, and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by clicking on the chat icon located in the lower right-hand corner of your WebEx window. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in a few weeks. You'll receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, John. Today's speakers are Drs. Keith Muller and Deborah Glueck. Dr. Keith Muller is a biostatistician specializing in the design and analysis of multi-level and longitudinal research. He is a professor at the University of Florida College of Medicine's Department of Health Outcomes and Biomedical Informatics. A fellow of the American Statistical Association, Dr. Muller has authored 2 current books on the theory and practice of linear models, as well as many other publications, including many collaborations in health research. Roughly half of Dr. Muller's effort has been supported by being a co-investigator or principal investigator on NIH-funded research. In addition, he's also served on standing and ad hoc review panels for NIH. Dr. Deborah Glueck is the Senior Biostatistician at the Life Course Epidemiology of Adiposity and Diabetes Center at the Colorado School of Public Health and Professor of Pediatrics at the University of Colorado Denver School of Medicine. Dr. Glueck has a career-long focus on power and sample size for multi-level and longitudinal studies and the analysis of longitudinal epidemiological cohort studies and randomized controlled clinical trials, including serving as a multiple principal investigator for several NIH-funded projects. It's my very great pleasure to welcome Drs. Muller and Glueck.
Thank you, David, for that kind introduction. It's an honor to be presenting today. You can see my title concerns multi-level and longitudinal studies analyzed with linear mixed models. And you've also seen our affiliations. Deb and I wish to declare that we have no conflicts of interest. We need to acknowledge support from a series of grants. We list the 2 most recent here. We're grateful for NIH's support. I also need to acknowledge, and Deb and I need to acknowledge, the team members who've played so many different important roles. Alistair McLeod is a software engineer that's led the current version of the software you'll hear about, and you can see the other names associated there, particularly Dr. Sarah Kreidler. The educational technology that we're going to mention and not present today was led by Dr. Albert Ritzhaupt during the development process, along with many students and others. My talk today involves the following bullet points. It begins with the idea that an original study is reproducible, and here I'm using the terminology the way NIH documents use that term. Is reproducible if a new sample of data collected under the original protocol is likely to lead to the same conclusions as the original study. To be reproducible, a study must have good statistical power. Now, advances in power theory make it accurate and fast to compute power for linear mixed models, but that's not enough. You also need software. And we're going to describe in some detail some free point-and-click software that makes it easy. We're going to use a longitudinal clinical trial illustrating the process, but we'll also give the directions for how to involve multi-level studies, cluster randomized studies as well. Now, no power software can cover everything, so there's room for future methodological work and also extensions to the software I'm going to mention. I always like to remind us that there are ethical considerations almost always in doing health research, because scientific knowledge being public and reproducible requires reproducibility. If the sample size is too small, a study may be inconclusive and waste resources. If the sample size is too large, then a study may expose too many participants to possible harm. In either case, if there are ethical considerations, risks to the participants in the study or to animals in the study, then it's an ethical consideration to get the study design correct. Not too small, not too large. Choosing the correct sample size requires a multi-level alignment. Conscientious study planners, such as I'm sure the people who are listening on this talk today, you automatically align your data analysis with your study design and your study design with your scientific goals as you iteratively choose the design and plan a study. I want to mention another step, though, and that is aligning the power analysis with data analysis. And that is not routine for three reasons. First, the statistical theory may not exist. And second, if the theory exists, there may not be good computational forms to do the calculations needed. And then finally, you need to have, I say easy to use, but it also must be accurate software. Until recently, in the history of science, linear mixed models lacked all three of those. But today we're better off. The core theory has been around now for a while. And I cite back starting 30 years ago, some of that theory. With no missing data, the mixed models that we're going to be talking about give a test statistic that has a multivariate name, and that's called the Hotelling-Lawley trace, and that's what our software does. But you can ignore that if you don't care about the statistical side. What matters is that with no missing data, the power results are exact in many important cases. If you do care about the statistics, and if you care about the math, as I do a lot, then you can use the references in the bibliography to find a path to the underlying theory and the computational methods that are equally important. It's very common to run simulations. In fact, I've been working on simulations and doing some research myself in the last week. They're great. For the purposes of designing a study, computer simulations take longer because you have to write and debug the simulation. You have to validate the simulation. That's a step often overlooked. You have to iteratively change the design as you interact with yourself and with other collaborators. And you have to generate enough points for a power curve if you're going to really understand the situation you're considering. A programmer working by herself or himself with a deadline is going to be vulnerable to mistakes in initial assumptions, mistakes in coding, mistakes in modules written by others, and an inability to validate with independent target values. So it's actually a difficult thing to run simulations to meet software industry standards. Straightforward to run a simulation. We give you easy to use and power software that's been validated to software industry standards. We have a point-and-click application that you only need a web browser to use. It's free. It's copyleft, so it will always be free. And it's based on a sequence of dialog boxes that are reflective of well-defined steps as to how one designs a study. The software development was funded by a series of 5 NIH grants to our group. The key features of the software is you can use it, anyone, anywhere can use it at any time. You only need a web browser. You don't need to be able to do any programming. You don't need to use mathematical notation. You can save a partial study design or a complete study design for later. This allows you to work in an interrupted fashion. It allows you to change your mind. It also allows you to create reproducibility of your science by storing the file to document what commands you gave the software so that you can reproduce that power analysis at a later time. All of the computations are done on a remote server. Glimpse covers a wide range of designs, and we list here acronyms of studies that you might have heard of, and if not, you can certainly look them up because they're the result of publications and are all funded by NIH collaborations except one, which is an NCI collaboration. American Cancer Society funded. So the TAG study was a cluster randomized study. You can sometimes call that a group randomized study, as in Dr. Murray's book. Observational studies with clustering. An example of that is ECHO consortium cohorts. ECHO is a large NIH-funded collection of projects. Randomized blocks design. An example of that is the CAPS Garden trial. Multi-level observational or randomized designs were used with the ENRICH randomized controlled trial. And in that situation, we had participant nested within nurse and nurse nested within clinic. Multivariate designs involve having outcomes that aren't in the same metric. So if we're studying cord blood chemokines in children, and there is a large project funded by NIH called the Healthy Start cohort. Some studies have clustering or grouping and repeated measures. And within the ECHO consortium is a study of micronutrients through pregnancy for women who are cohort members. So one of the strengths of the software we're going to talk about today, by illustrating with longitudinal designs, actually the designs can be only clustered, they can be only longitudinal, or they can be the combination of both. Our track record is based upon peer-reviewed publications and funding for those peer-reviewed publications. At this writing, 288 people have published peer-reviewed articles citing our software, and they in turn cited $100 million in NIH grants. The softwares were funded by 12 institutes and centers. The topics include all 16 medical subject headings. Last year, Google Analytics told us that 10,000 people visited our website. But I'm particularly fond of the next number, which is that we know from the software talking to us in Google Analytics that 2,700 different power and sample size analyses were completed. And 2,700 distinct people completed power and sample size analyses. Most of our usage, a big piece of our usage is from US universities, roughly 17% from a brief sample we did. And only 20% of the users had foreign country codes, although that's a good thing. We're supporting people in Australia and Europe and many other places. So we're going to do an example longitudinal study. It's a proposed randomized trial based upon a previous group, and this was stimulated by collaborations with colleagues in the College of Dentistry and was associated with NIDCR funding. The primary outcome of the trial will be the memory of pain reported after a root canal. So this is about a visit to the dentist, but we're going to take the pain out of that because we're going to show you how easy it is to design the study. The memory of pain is going to be recorded at 0 months, 6 months, and 12 months, so we have 3 repeated measures. They will be included in the study if they have a coping style with 2 features. The first feature is they feel they don't have control. They feel they do not control the situation, but they wish they had control. That sounds familiar to me, going to the dentist. We're going to have 1 of 2 treatment arms, sensory focus or standard of care. I like to use flowcharts, software engineering flowcharts, to describe a study design. So we start where it says randomized participant and can then be randomized either up into sensory focus or down into standard of care. And then we go across time to 0, 3, 6, 12 months. And once the data have been collected, we stop. What we hope to see happen is that the blue line is the memory of pain under standard of care. We're hoping that if we train people with sensory focus, the memory of pain starts a little lower, and more importantly, gets much lower later on. Participants will be included if they have a particular coping style that I mentioned earlier. From our previous work in the clinic in the dental school, we expect 30 patients per week available. And the previous study from which we're going to be using some of the numbers had a 40% consent rate. So we need to know a type 1 error rate. We need to know the desired power. And we're going to consider 3 different powers. And we need to know something about loss to follow-up if we're going to make a realistic power analysis. So this is the front screen of the Glimpse power and sample size software. In order to get there, you'll go to the website that I'll tell you later, show you on slide 65 and slide 70. And you'll be asked to create a login. And once you do that, you come to the first page. Now, if you are visiting for the first time, you'll start a new study. But if you've started a study design previously and have saved it, then instead of choosing new study, the second from the bottom button, you could, if you've got a previous study partially done, use the upload button. For a new study, pick a title, click the power or sample size. Now, I'm going to give you a sample size because that's what people ask us most about. I am personally a big fan of power values and power tables and power curves, as I'll illustrate later on. You can do either, your choice. In our case, we're going to specify 3 power values, which we're allowed to do a large number. And if we're going to be targeting mixed models, you should know that your default choice should be Hotelling Wally trace. For those interested in the statistics, you can look at the technical references we give and find out why. Type 1 error rate. It's very common to use 0.05. I believe that that's actually quite liberal and would typically use much smaller than that, but we're going to use 0.05 because of its commonality. We need to enter the outcome variables. Not only does Glimpse allow repeated measures and allow clustering, we can also have multiple outcome variables. In this case, we're only going to have one, the memory of pain. And next, we get to define repeated measures. I've put the study design back on this screen to indicate, remind us, we've got 3 time points. And since in this case, that dimension of repeated measure is across time, that's what we're going to call it. And time is numeric, but we could also have a categorical repeated measure. So your repeated measure could be a concentration level of a toxin in different organs of the body, for example. And that would be a categorical repeated measure because the levels might be liver, spleen, brain. We have 3 repeated measures. And we get to choose whatever times we want. So in this case, we put in 1, 2, 3 because they're equally spaced. But if in fact you were measuring at day 1, day 27, and day 132, that would be fine. And we'll provide the appropriate trends contrasts for you. So then we get a summary screen in which we ask you to review what we said for you to verify that it's right. And if it's not, you can always go backwards. You've got green arrow to the right and gray back arrow to the left, and you can edit things and change them in an iterative fashion. In this case, there's no clustering, but I want to point out that it's extremely easy to add clustering. We click the Add Clustering button, and what we ask for each level of clustering is what is your cluster size and what is your interclass correlation coefficient. So if you have those 2 numbers, you can add a level of clustering. We allow currently up to 10 levels of clustering. So 1, 2, 3, we've got you covered. And a cluster size can be any size. That required some additional work to make that happen, but we did it. A fixed predictor, in this case, is the treatment variable, something that varies between independent sampling units. And so we're going to call it treat because we are convinced it's a treat to go to the dentist who cares about whether or not we have pain. And here we define what type of data we have and move on to define the group. So in this case, it's just a nominal indicator, treatment, not treatment. And so we're going to define the groups and we type in the names treat group and control. We choose the contrast. And when one defines a repeated measures design with one between group factor, which is treatment versus control, and one within person factor, which is time, actually had 3 times and 2 groups, then the natural, most complex hypothesis is the time by treatment interaction. Our software presents the possible effects that your design has defined and lets you choose. So the default is treatment by time, but you may not be that excited about it. You're maybe doing this design to be careful, and what you're really hoping for is a main effect of treatment. And if so, you could choose to power the study in that way. The default choice is, again, what people do most commonly, which asks the question, are the differences between the means all 0? But we allow you to choose custom contrast if you're interested. Similarly, we allow you to choose testing of a mean against a non-zero value. An example of that would be if we're studying fever and what we're hoping to do is bring people back to normal, we may be interested in testing the hypothesis that the mean of the treatment condition is in fact 37 degrees centigrade. We wouldn't want to test mean temperature to 0. Being mean temperature 0, you're probably not going to, the participants are not going to be too happy about that. So time by treatment interaction, that hypothesis corresponds to this hoped for scenario in which the blue line is standard of care and our pain memory diminishes over time, but we're hoping that by giving sensory focus training, we can diminish the pain memory much more. We have to tell the software about our relative group sizes. It is possible that you want to do 2-to-1 randomization or 3-to-1, or perhaps you're powering a study that is a case control study in which you don't want to use, for various reasons, 1-to-1 randomization, 1-to-1 recruitment. And so we allow you to do that quite easily. So here we have the means that we're hypothesizing based upon a previous study that we cite in the slides. And we believe, and these means correspond to the hypothesized picture on the previous slide. So this picture corresponds to this table of means. And never trust a statistician to do arithmetic on the fly. These 2 numbers should be negative. So less pain is better. And so we like numbers that are smaller. And so that leads to these things. We want negative direction of effect. And so this is the difference at baseline, and then the hypothesis is that the difference between baseline, between sensory focus and standard of care goes from 0.9, from negative 0.9 to negative 1.5 to negative 2.1. And then at the end, of course, that change over time, the interaction is then negative 1.2. So we type in these numbers. There are various friendly things it will do, the software will do to make this task easier. But for right now, it's just a matter of typing in 6 numbers for this example. and it arrays them in a way that you're accustomed to seeing as a factorial table. We give you a tool called scale factor because sometimes it's important to consider mean differences larger or smaller than what you've hypothesized. If we knew the answer, we wouldn't have to run the study. So there's always a good deal of speculation and what if and guessing in terms of doing a power analysis. This is one of the ways you can account for uncertainty in your planning process. So the sources of variability and correlation in a study design are, to a statistician, technically, and they mean this in an almost loving way, nuisance variables. But to the scientist and the statistician or whoever is designing the study, that's truly a nuisance. We have to come up with good values because if those are credible values, then we'll have a credible study design. We have to recognize that repeated measures within a given participant will be correlated and that outcome measurements will vary between participants. Here, Deb and I have given you a paragraph of text in which we cite some previous research that give an example of going through the literature to find examples of correlations and variances in order to fill out the results. So in this previous study, at 1 week, the correlation between the 1 week and 18 months pain intensity was 0.4. And we're going to assume that the correlation between 18 months and 12 months will be very similar to that. And that's a guess, okay? It's part of the classic guessing process that sometimes one is forced to do in doing power analysis. But it is a credible value because that 0.406 was a published result in a peer-reviewed journal. Similarly, we're going to assume that the correlation between 6 and 12 months apart is not that different. And we're comfortable in that because this original correlation was over 18 months. So we would think that we would have even more stability over shorter time periods. Similarly, we can look at a previous study from 1995 on this pain scale in which on this 5-point scale, the standard deviation was 0.90. And that was during a root canal procedure, just like we're talking about in planning the study currently. So we type in the standard deviation. By the way, one of the best ways to do a wrong power analysis is to confuse standard deviation with standard error. It's very difficult sometimes in reading a journal article to know what is being presented. So please keep in mind, is it a standard deviation? Is it a standard error? And sometimes it also, the same issue arises with respect to, did they give you a variance or did they give you a standard deviation? In the case that we're considering, we're assuming that the uncertainty, the variability, the spread, the dispersion, the standard deviation, the variance, whatever name you want to talk about, the wiggle is roughly the same across time. And so we put in ratios of 1 to 1 to 1. If we were studying the acquisition of vocabulary in children, then we might expect that to change. If we're looking at a growth process in which you reach an asymptote, then you would think the wobble would be great at the beginning and get smaller at the end. And so we might see 3 numbers that were 3, 2, 1. On the other hand, if we're studying a disease process in which the performance of the body is deteriorating, you might find very little variation at the beginning and then greater and greater variation towards the end of the measurement periods. So I can see these being level, I can see them getting larger, or I can see them going down. It's a scientific question. The software makes it easy for you to account for that. Correlations. If you get the variances and the correlations right, then you're doing a valid power analysis. We give you the ability to enter correlations, and we've given you the logic in previous slides where these numbers came from, but we also give you some structured choices. And we don't have time to talk about that today, but we can help you make up a scientifically reasonable correlation matrix if you could give us some basic information. In addition, because you may not be certain that the population you're studying is as variable or not as the one from which you got the standard deviation, we can put in scale factors that say, what if the variance is bigger than what we saw? What if it's smaller? That's it. We've typed in everything we need to do a power analysis for a longitudinal randomized clinical trial. And so we can now hit the calculate button. And once we do that, we get our results. A key feature there is that we can save those results. The save button is available at every screen previously. You can stop at any time. Somebody can say, let's go get a coffee. Your friend can show up at the door of your office. It doesn't matter. Hit the save button and come back to it later. Furthermore, that provides you the ability to document the power analysis later so you can reproduce it and meet the standards of reproducibility science. So here we have 3 powers, and we asked for 0.85, 0.90, and 0.95. Instead, we got powers of 0.869, 909, and 957. And the reason for that is that we provide a physically realizable design. We don't ask you to take a person and chop them into pieces. We figure you're going to keep people whole. And because you ask for a balanced design, this also, in 2 groups, this has to be an even number. So the program thinks that through and tells you the closest design to giving you exactly 0.85 power actually gives you 0.869 power, or 38 for 0.9 and 46 for 957. I'm going to skip this slide, but I want to tell those of you who like the math, hey, it's there, and you can get your hands under the hood by looking at the articles. And in fact, the program can even tell you some of what it was doing in the back behind the scenes. So if you needed to avert your eyes there, that's okay. Here's a summary of the sample size calculation that we've done. We planned a repeated measures analysis using the Wald statistic because we're going to do a mixed model analysis, and we tested time by treatment. We had a standard deviation of 0.9 for memory of pain scores and a correlation of 0.5 roughly. We knew that the correlation at 12 months we thought would be 0.4. And we think we need around 38 participants to detect a mean difference of 1.2. But let's think about that situation. So there are 3 lines here. Each of these is a power curve. The vertical axis is power, the probability of detecting a difference that's real. The horizontal axis is difference between the means. And so, again, I'm not using a mouse because we don't have a pointer in this software. If we're interested in what is the impact of 3 different variances, then we've drawn 3 different power curves here. The purple is what if you're lucky and the variability is half as much? That's the purple line. The blue teal line on my screen is the one in the middle. That's what if you got the variance right and it's really the standard deviation is 0.9. And the one on the right is what if the variance is twice as large? And so that gives you less power. So the gold line is the least power because it has more wobble. The purple line is the most power because the wobble is real tight. And the one in the middle is the one we thought it was. If we're looking for 0.9 power, we can have 0.9 power against what are radically different mean differences, because the intersection point for the purple curve is at about 0.7, and the intersection for the teal middle line is about 1.0, and it's about 1.5 for the gold line. So it really makes a difference what's going on as to which variance you have. And that's why we have to do what ifs. What if the variance is more or less? We also need to deal with missing data. If we have 25% loss to follow-up, then we need to inflate that sample size by dividing by the percent follow-up, and then we have to turn it into a physically realizable design because we don't want to chop off 0.3 of a person. And then we have to have an equal number of groups because we know that power is actually maximum when we have balanced group sizes. So that ends up 52. So we started at 38, and then we put it at 52. As an NIH study section reviewer, explicitly making this paragraph present would give me comfort that you are proposing a study that's likely to succeed. And so you would write this up in the grant proposal in the following way. 25% loss to follow-up means that in order to achieve the power we're actually going to, that we want, we're going to start with enrolling 52 participants. And because we know we get 30 patients per week and we expect a 40% consent rate, then that will lead us to enrollment period time in 5 weeks. On this slide is the website where the material, the software is available. And in addition to the software being available there is a free short course. It's a short course we've created and conducted with over 200 scientists with NIH funding for an R25. We also, as part of that process, gave a 2-credit course at the University of North Carolina. And there are roughly 1,000 slides. There are homeworks. The answers are there. There are screenshots, video lectures. You can look at them individually or as a whole. There are also tutorials, theory articles, applied articles. What's not available is we only cover a subset of mixed models. We don't allow certain kinds of incomplete designs, although we allow unbalanced designs in many ways. We only can have simple covariates. We don't allow unequal cluster sizes. We don't allow missing data. You have to deal with that as a separate issue. We don't cover binary data. It's probably one of the big limitations. There's no power software that covers everything. So there's much room for methods work, and there's also room for extensions to the software. We will follow and do what users ask us to do. The preferences of users will guide us. We are seeking funding to continue the project as we speak. In reviewing what I've talked about today, I want to say that an original study is reproducible using the NIH interpretation of the word. If a new sample of data is collected using the original protocol, that the new data is likely to lead to the same conclusions as we saw in the original study. We need good statistical power for that. We have theory to do it, and the software I've talked about today makes it easy. We've illustrated the process with a longitudinal trial of pain, the memory of pain. Our graduate students were fond of the phrase, the only outcome is the memory of pain. But I hope that glimpse the memory of removing pain, because we hope that the power software makes it easy to do the designs we cover. We can't cover everything. There is room for future methodological research and extensions to the software. And with that, I turn it over to Dr. Murray, who has said that he would moderate the questions that I've heard.
Thank you, Dr. Muller. A terrific presentation with hundreds of people listening and questions pouring in. I will try to go through some of these. So in the example that you worked with, you were able to use means from previous data to estimate the effect size, but what if you don't have previous data? You don't have those kinds of estimates. Can you use values for Cohen's d, for example? Can you just enter those kinds of things for the power analysis?
One could. I am personally uncomfortable with that. There are articles by Russell Lenth, that's Lenth, in the American Statistician, in which he gives what I think are cogent and compelling arguments as to why it's best to consult your inner scientist and answer the question that my first computer science teacher taught me. And it sounds like a dumb question, and it's a question that I cherish and have carried with me for the 50 years since I first heard it. How big is big? If we're talking about pain, if you're studying pain, you have a sense of what that means. You have a sense of your scale. And so use clinically meaningful differences to determine what means to type into your mean table. Draw a sketch as to what you think will happen in the units you've got. That would be my preference. I find the Cohen approach equivalent to getting into a car and putting it on automatic pilot. That's a dangerous thing these days, at least.
Thank you. Is the standard deviation that you referred to the standard deviation of the difference, or the standard deviation of the baseline value, or the standard deviation from
Good question.
Population measure?
It needs to be the standard deviation within a group of the outcome at each time. So think about it at baseline. What is the standard deviation of the outcome variable, in this case, the measurement of pain at baseline?
You used a figure for percent loss to follow-up, and one of the folks in the audience asked, how did you decide on that percentage that was lost to follow-up?
Clinical experience. So the citations that are listed here for the various scientific articles, by the way, Dr. Henrietta Logan was one of our collaborators, and she was one of the authors of the paper. And so she had actually done the earlier studies, but if we were running a new study and didn't have her on the team, we could look at those published papers. So the right answer is, if you don't have experience in your own laboratory, go to PubMed and see if you can find out what the experience is from others in a similar arena.
Another question, can you use the software to do sample size or power calculations for observational studies?
Yes, absolutely. When we define the groups, those are simply names that we provide for the groups. The groups may be naturally occurring groups. They could be people that entered the stadium from the west gate versus those who enter from the east gate. They could be defined by pre-existing conditions. They could be defined by disease. So absolutely, randomization is not necessary to use this software. Randomization changes how you may interpret the results. It doesn't change the data analysis, the presence or absence of randomization.
Is it okay to share the materials available that are associated with your short course?
Yes. The correct phrase and process and rules, oh, it's slide 65, is that this is a fair set of training materials. There are rules of engagement which one must follow in using them. And so if you're not familiar with the FAIR principle, please look it up. NIH supports it strongly.
When you say that the software doesn't support high dimensional problems, what does that mean?
More accurately, high dimension, low sample size is a situation in which we have more outcomes than we have independent sampling units. We have co-authored research on that, and there are methods in the literature on that, but currently we don't allow it. So that would happen if you're looking at a metabolomic analysis with 85 outcomes and 13 participants. That would be high dimension, low sample size. But we do allow large studies. We work with large studies, not a problem.
Okay. One of our viewers asks, when is it appropriate to use a general linear mixed model and when is it not?
The terminology general linear mixed model is narrowly concerned with data that we can assume that the residuals from the model are multivariate Gaussian, are, quote, normal in their distribution. So that's why when I mentioned the limitations, we don't cover binary outcomes, we don't cover Poisson. Generalized general linear mixed models deal with those kinds of outcome measures. And we also don't cover survival outcomes. There is software for survival outcomes out there.
Do you have any recommendations for how to calculate sample size in studies with binary outcomes?
None that I feel I can defensively publicly state. I do that, and I have my selections, but there is a great deal of uncertainty in the binary world as to what data analysis method is correct. And the correct answer to that appears to depend heavily upon the particular study design you're talking about. Associated with that, there have been not as much work on power and sample size for binary. It is an area that we have an interest in, but I personally don't feel that I have a definitive answer to just say what's the best way to do it. Because first you have to decide what's the best way to do data analysis. I will caution you that some of the popular methods for binary data analysis can perform very poorly in small sample sizes. In the context of clustering, the sample size that matters is not the number of observations, but the number of clusters. So if you run a randomized cluster trial with 20 cities that are involved, and that's your sampling unit, you have n equals 20, even if you've got 1,000 people in each cluster, you're really at a sample size of independent sampling unit number 20. So some of the binary data techniques don't work very well then.
Different kind of question. What's the upper bound on the number of repeated measures?
Currently, we limit it to 10. I know that there's an interest in intensive longitudinal design. Oh, by the way, we allow 10 repeated measures, and you can have 10 dimensions of repeated measures. We could easily change that if users wanted it. There are some scientific considerations and statistical considerations that can't just be handled automatically. And so we've been, and yes, I'm aware of the interest in intensive longitudinal designs.
Right, and that was the source of the question. You indicated that one of the screens allowed the user to pick which effect that they wanted to power on. Sorry.
May I go back to that, David, and make one final comment about the intensive longitudinal?
Mm-hmm.
I will give you consulting advice, free consulting advice, and it's worth what you're paying for it. My default idea going into an intensive longitudinal case is to convince the investigator to consider creating a composite score out of the intensive longitudinal dimensions and come up with a handful of computed scores, linear, quadratic, cubic, for example, or fit a nonlinear model, and do a dimensional reduction by thinking, not by computation of components analysis.
Thank you. And that pushes me to a different question than I was going to use. Can we estimate the sample size using glimpse for the random coefficients models? These are sometimes known as growth curve models, where you're fitting a slope to repeated measures rather than modeling them categorically.
Yes, but first of all, if you take the growth curve model, the growth curve model corresponds to choosing custom contrast inside glimpse. There was a screen that I brushed over. If you're doing a growth curve model, let's say you have 10 repeated time points, and you just want to do a linear, quadratic, and cubic trend, then the default in glimpse, it's going to do a multivariate approach. It's going to give you all 9 trends. If you only want to do the linear, which I don't suggest, if it's human behavior, I'd want to go up through at least cubic, and you just want to do linear, quadratic, cubic, then you can specify a custom contrast, and you're there.
All right.
There is discussion of that from the mathematical side in the Glueck-Muller 2019 paper.
Okay. I want to tip my hat to Dr. Glueck, who is answering some of the questions in the chat box, even as you and I are having this conversation. So she's helping us out. And she's providing links to things that you're referring to, which is extremely helpful.
She's a winner.
Yes. So there are lots of packages out there that do sample size calculation. SAS does it, PASS does it, G-Power. There are Shiny apps. The NIH has a website that I've worked on that does sample size calculations. What are the advantages of Glimpse over these other packages or other sources?
Some of the software that's out there that's free software has not been validated. I would be very cautious. The commercial software is always validated to a high standard. So that's number one. Number two, relative to PASS and SAS, we do lots of designs they don't, especially combinations of clustering and longitudinality. We make it easier to do clustering with continuous outcomes. The Shiny apps, all I would say is look, have they published the methods and have they published validation studies? I recently saw an article by White in a 2019 Conservation Genetics in which the authors discovered that an article that had been published about a multiple comparison technique, that the code was wrong, and there had been 600 papers that cited that wrong code in the subsequent years, and it was a dramatic difference in what the data analysis should be, yes or no, and that was a classic example of here's a piece of our code to do it.
Thank you. That's a good warning. In your example, individuals were randomized to the 2 study arms, and I think they were seen by a dentist. It's possible, I suppose, that there may have been more than one participant seen by each of the dentists, or at least by a bunch of them. And that would create correlation in the observations taken by patients who see the same dentist. Can Glimpse handle that sort of situation?
Yes. the dentist then becomes a clustering dimension. And the question then one has to sort through is at what level is the randomization? Is the randomization within the cluster or between the cluster? Glimpse is very good at doing randomization between the clusters, designs like that. It's actually straightforward to do randomization within clusters as long as the cluster size doesn't get too big, because at that point, if you want to do randomization within clusters, you should treat the cluster as a repeated measure because you'll want to do a contrast within the cluster. If that doesn't make sense in 3 sentences, drop Deb and me an email and we can point you in the right direction.
Can we use Glimpse to do power analysis for multi-arm trials? Your example had 2 arms.
Absolutely.
What if we have 3 or 4?
As many, you could have, I believe we allow you up to 10 arms. And you can do factorial. You can do, I don't know, again, probably 10 factors. You can certainly do a bunch of factors.
Does Glimpse support sample size calculation for step wedge or crossover designs?
Crossovers correspond to actually a special case of cluster designs. And you could set up crossover designs as a repeated measure. So yes, you can definitely do crossover designs in Glimpse. We don't support stepped wedge. I'll speak for myself personally. I'm rather uncomfortable with the way stepped wedges. I'm uncomfortable with stepped wedge designs. I think it's extremely easy to have problems with making valid inference, and I'm particularly concerned about power of stepped wedges relative to alternatives of completely randomized, group randomized trials.
Right, I agree with you on that point. When I talk to people, I always say individually randomized controlled trial if you can do it. If there has to be some intervention agent who interacts with multiple participants, like a dentist in your study, then we can account for that clustering. If you're going to randomize groups, use a parallel group randomized trial. And step wedge is the last choice in my hierarchy. I think people jump too quickly sometimes to step wedge, thinking it solves some problems that it doesn't really solve. Technical question. You have recommended to me using Kenward-Rogers degrees of freedom when I'm doing analysis that involves complicated mixed models. Is
Yes.
there any way to use that in a sample size calculation or reflect that plan in the sample size calculation?
We've done it. The hidden reason, let me see if I can. Why did it jump so far up? Okay. I don't know why my computer is jumping 40 screens on me. 3, 4.
Sorry. Was it one of the test options instead of the Hollings-Lawley trace?
Yes,
Is that where you're
Hotelling-Lawley trace. Yes, the Kenward-Rogers test statistic reduces to the Hotelling-Lawley trace, and therefore, by choosing Hotelling-Lawley trace, you are aligning the power calculations with the Kenward-Rogers degrees of freedom. There is additional technical detail in the Glueck-Muller 2019 paper.
Great, thank you.
So,
we are at time, and I still have lots of questions. I'm afraid we're not going to get to them all. terrific audience participation. Deb has been doing a great job trying to answer as many questions as she could, and you've done a great job answering them as I've been firing them at you. But I'm going to have to stop and turn it over to John to wrap things up. Dr. Muller, Dr. Glueck, thank you very much.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. You will receive an email link with a link to the recording when it's available. Thank you and have a great rest of your day.